So I want to talk about Accelio. Accelio is started as a kind of experimental tryout to accumulate all kind of experiences that we had in Mellanox when writing applications. Experiences with optimization, experience with application requirement, and we try to write some kind of a new API that will enable us to write the code once and use it as reusable code for many times. It's grown and get matured, and what we got for now is an high performance, transport independent, a simple to use, reliable messaging, and RPC library for accelerating application. Our attitude towards this problem was that we came up from the application side and not from the hardware side. We try to understand what applications are needed. We find that many of the applications are using, the proactor or reactor kind of design patterns. They have some kind of event loop, which all the work is being doing by this event loop. And what they will actually need is the networking to be seamlessly integrated into this loop and provide them network functionality without having to write a lot of code. They don't want to mess up with optimization and all kind of issues that are on the lower layer. They want to focus on their application and get faster to market. So we try to analyze those requirements and wrote the API. And I will present it in a few slides. The API now has a user space API. It has also a kernel space API, which means that a kernel client, a client which is written by Accelio kernel API, can talk with a user space API, and the user space API can talk with kernel API, and you can do all the mixture between them. The wire protocol is the same. The API has 90% compatibility between the kernel and the user space. That was because of differences between kernel and user space, and not because we did not want to support them. The API is written on C, so it can be used by C++. We had a Java binding to this API. We plan to do a Python feature in the future. So what we did over there is we took optimal usage of the CPU, the memory. We wrote code that is allocating memory, and it's a NUMA aware. It's doing NUMA aware allocation. It's use affinity for CPUs. It's use affinity for CQs, and it maximizes the usage of the resources of the modern architecture of the computer. So it's also built for fault tolerance. It has transaction reliability and load balancing. It has integrated into open sources by now. We have a HDFS solution. We are working with the Ceph community to provide the solution for Ceph. And we have several commercial and storage products that are now being developed and will be released in the few next months. So what's different in Accelio is that it's a completely an open source code. It's a community project. It's currently not a product that provided by Mellanox. We provide all the support and everything else, but we initiated the project. But we are looking for other strategic partners to get into this project and help us develop this API. It has a website. It's called accelio.org. The code is on GitHub. Everyone can download it and start playing with it. And it has a community and project backtracking on launchpad.net. We hope that other companies will join us and add support for this API. So the key feature for this API is that it's focused on high performance asynchronous API. All the API is asynchronous, which means that completion are getting returned to the application by callbacks, application register callbacks, and completions are getting by those callbacks. It says reliable messaging delivery end to end. If we know about TCP, for example, it says reliable messaging, but it's on the transport layer, which means that you are sending a message, and it does not guarantee that the application on the other side aware that the message is not received, and the client side is also not aware that the message was not sent. So in Accelio, every message that you are sending is reliably delivered to the other peer. If it doesn't deliver to the other peer, we will get notification, and the messages will be returned to the application itself for other treatments. We offer two models. We have a model of request response, and we have a model of send receive. We mapped a lot of applications, especially in the storage area, and most of them are using request response models. They send a request to the peer, and they expect a response to get back. So most of the Accelio goal was to provide an efficient request response mechanism. As I said before, it's maximize the hardware resources. It's doing resource abstraction, and you are not working with directly with a QP. You are working with a logical object that is called connection. Multiple connection can work with the same QP, and that's end up with scalability and high availability. It's designed to maximize the benefits of RDMA. We know we gained a lot of experience with RDMA optimization, so we know how to do hardware offload, coalescing, and other mechanism to get the maximum performance that we can in the RDMA, for example. The API support multiple transport. You write once and you get used by multiple transport. Moving from one transport to another is transparent to the application. It's very simple, and you get the same code for both transport. Transport is a pluggable features. That means that other transport API that you want to add, it can be added, and that's it's quite an easy task to do that. We write it on RDMA at the beginning, and then we work on the TCP. Currently, the TCP is not released, but we are working on it now, and we see that writing this plug was not. It was not task consuming. It was quite easy to do that. It has small messages combining, and you can send large messages combining. It provides a true zero copy end to end. The application sends a buffer, its own buffer, and it's get into the peer side, and it's true zero copy. There is no copy inside the API. There is no locks in the fastpath side of the API, so no contention, no locks. And I will show a performance result. Will show that we're getting very good performance result. So as I said before, Accelio architecture is provided with three layers. The first layer is the API. The API is very thin, is very small, and it can provide most of the application requirements. It's an RPC one, and it's providing also a multi-queuing API. Under this API, there is pools of connection and session management, which maximize the CPU core usage. It provides parallelism, high availability, and migration. And it scales the network bandwidth. So the last thing is the transport protocol. So transport are pluggable. We started with RDMA as a native protocol, but we are now working on the TCP transport. It can be done to other transport shell memory. So you write once the API code, and you get support for multiple transport. So how transaction flow it look like? So there is side A, which is the initiator, and there is side B, which is the receiver. The side A is issuing request. The message is comprised of header and the data. It has two parts of the data. Since it's a request-response model, it has data in and data out. The data in is a vector. It's a simple IOVec, as you know it. It's address, you get length, and you get area for a opaque memory registration object. Usually application prepare a pool before they start to work. They prepare a pool of those messages, and messages can be recycled, and so registration is done once. So application is preparing the request. It fill up the header. It can fill up the data that it wants to send on the outside of the message, and it can put buffers. If it's supposed to receive data, it can put already buffers, its own buffer that were already registered on the inside of the message. So data will be put into with RDMA operation directly into this inside of the message. So when message is ready, you send the requests. We mean that inline data is the header. The header is always being copied into an internal buffer. And we usually work with send-receive operation for the header. We send the request to side B. We send also the keys for the data that we want to operate on. So side B now is listening for incoming messages. It gets a request notification with data. It can take the data and do it can process that in an asynchronous way. So when data is ready, it can send a response back with return data. So the data is sent back to the client side. The client again receive response notification, and when the client finished using the data that it received, it's calling a release to release this data that was allocated for him. So everything in this flow is going with a zero copy mechanism. There is no copy at all for that. The application and the library share the memory between them. Another issue is that it's asynchronous, so you can issue multiple requests at once, and they are submitted in parallel. All the credit management, all the workflow, flow control is being handled by the library. For example, the application can send as many messages as it can. So messages are being sent to the other side. If there are no credits on the client side, the messages are being queued and will be sent when credits are coming back. So how it looks like. I want to show you how simple writing to Accelio is, and we start by the simple application that we write over here. We omitted some of the line for brevity of the code, but as you can see, it's quite. This is the main, and it's quite simple. So on the main side, what we are starting with is we are creating an object that is called a context. The context is actually the event loop of the mechanism. Context itself contains an epoll, and all the events are eventually coming to this epoll. So you create an object that is called context. The next thing that you are doing is creating a session. A session is can be a type of a client session, or it can be a server type of a session. There is a parameter that's called attribute. On the attribute, you set a certain structure of file operation that you are supposed to get your notification on. For example, when you are receiving response, you put on response callback and set it on the attribute operation. Addresses are used by a URL. So that means that on the URL you put the scheme, which can be RDMA or TCP. You have the address of the remote peer, you have the port of the remote peer, and you can set a resource that you are going to work with on the remote peer. So eventually, when the remote peer getting this URL, it can decide upon the resource, the source address, the port. It can do some kind of hashing and decide whether to accept the message or to reject it or to redirect it. I will talk about it on the server side, but let's continue with the client side. Then you are doing a connect. Note that connect is an object that provides you a connection. Connection has to do with the thread. You can do a multiple connection for each session that you have. So you operate on connection from the same thread that you assigned it to. So the thread is designated by the context. And the last parameter that I want to talk about is a user context. You can provide your own context, and that will pass to each of the callbacks when callbacks are being called. The next thing you are doing that you are preparing your own message and you are issuing a request. Please note that currently the event loop did not run. Nothing is running in that. There is no connection. There is nothing. It actually just created the structures. So you can send a request, and the request is being queued. And the next line is that you are running the dispatcher, the event loop. So currently, the dispatcher is running, connection is being established, and the message is being sent to the peer side. And the last line is the exit phase. When the loop is a blocking function, when loop is ended, then everything is destroyed and being cleaned. So on the client side, let's see two of the callback that can happen over here. So, for example, there is on session event. Session event, there are 5 or 6 events that can happen through a session. For example, one of the events is that connection was teared down from some reason. So, if connection was teared down, you can destroy the connection. And when all the connection of the same sessions were teared down, you get a session teardown event. So then you destroy the session, and usually what you do in this stage is stopping the event loop and getting out, and the client is going and exiting. So the second callback is on response. When you send the message to the server side will respond it with its own response. And you will, when response is coming to the client side, you will get a response message. So what you are doing with the response, you are processing the response, and when you are no longer need a response, you call release response to release the resources back to the library, and then you can issue a new request with that resource. Again, the API is asynchronous, so you can issue multiple requests, multiple responses. This is just an example of one message ping pong, and of course, it's the very simplistic way. So let's see what's going on the server side. On the server side, again, you are creating a context. Again, context is designating the thread context that on the server it's provide the event loop the dispatcher event loop. You bind the server, you provide him the server operation structure, you provide the URL that it's listening on, and you provide some kind of user application data that you want to pass to all the callbacks, and immediately after you run the loop. So the server is now in listening mode. It's waiting for events to come up, And when the loop is broken, there is the exit phase that you destroy all the resources. The first event that will come on the server will be a new session. New session was arrived. You can accept the session and handle it on the local callback, or you can forward the session to be handled on backend threads. That's a possibility with this API. You can also redirect the connection to be handled on another server. So that you can do a scaling with one server to another server. Application can also reject the request and put some information why the session was rejected. When coming new requests, there is a callback. Again, on the server side, we process the requests and we prepare a new response to answer to the requester side. We take as you can see, we attach the original request to the response, and we send it as a response. You see that there is no connection on the sending response. It just go back with the same connection that it come from. So connection to connection, there are connections are not moved between threads. So we don't have to put any locks between the calls. Everything is on the same thread that it's starting from and ending up on. So let's see what we did with integration with other application and projects. Accelio is a C library. We do some work with the Ceph community now. We plan to work with MongoDB. And we have, with the C code, we have other storage vendors. I cannot disclose them, but we're working with them now, and there will be a solution on the market in the few coming months. We wrote a binding with Java code. It's called JXIO. It's also an open source. You can download it from the Accelio website. We provided a solution with Hadoop, with HDFS. And I will talk about it in a minute. Accelio is currently adopted as an high performance and low latency reliable messaging. It's very simple and taking a customer very quickly to market with that API. So let's talk about some use cases. We wrote on the kernel side of Accelio, the first use case is a kernel side use case. We wrote Accelio, or accelerated network block device. Accelio has features that help providing facilities to this block device. The first thing about this block device, that it's as a multi-queuing implementation in the block layer for high performance. It utilized the Accelio facilities, such as hardware acceleration for RDMA, zero data copy, the lockless design, and optimal CPU usage while doing a reliable message delivery. We did some testing with that, and also the code is open source. It can be achieved in the GitHub Accelio website. So the second use case that I want to show you is the RAIO. What we try to do over here is taking the standard AIO library. It has a few APIs like IO submit, which provides asynchronous IO operation, and we wanted to remote them. So on the client side, you can start opening, for example, FIO benchmark utility, and the API is very similar to libaio, so you can plug in this FIO engine, which emulate the AIO operation. And on the other side, there is a RAIO server, which is linked to Accelio library, and from the other side it has backend that supports multiple file systems or a RAM disk or any kind of operation that AIO can be used. The network itself, as you see, we used multiple connections and thread to accomplish that. And on the right table, you can see that we got IOPS of 2.5 million IOPS on read operation, and we got a very low latency of 5 microseconds. All those results were measured by the FIO, so we didn't measure them. The FIO has very good benchmarking statistic abilities, and we use that to get those numbers from. The next use case that I want to discuss is JXIO. JXIO is a Java binding to XIO, and it provides the first public RDMA API in Java. JXIO is a Java wrapper for Accelio. It's also an open source, which you can download and play with it. It preserves the Accelio zero copy and the performance all the way. Every C struct in Accelio is represented by a matching Java class. We reached 1.5 million transactions per second. Transaction means request response in Java, which I don't remember hearing such numbers in the Java area. This API serves as the basic for Mellanox solution to the HDFS RDMA acceleration solution. And we are working to release that in the near future. This is a test configuration. I want to show some graph. You can see the configuration. I just want to speak about the PCI, which is important. We have a Connect IB, which is 16-lane PCI Express, and we have Connect 3 Pro VPI, which is H-lane PCI Express. And we show you some of the results that we got with that. So concerning bandwidth, as you can see, with one IO thread, when we are reaching 4 kilobyte message, we reach the we reach the line rate. We reach the PCI Express rate. That can be 6,000 megabyte per second. That's with Connect IB API. With Connect 6.3 Pro, we reach a little bit lower, and again on the large message size, we reach almost the line rate. For two threads, you can see the amazing result that we got. We took a Connect IB, we put one thread on one port and the other thread on another port, and we reached 12 gigabyte of gigabyte per second, which is 100 gigabits per second with Connect IB. That was on almost a standard computer with 2 IO threads. I think that it's a quite amazing number. As for transaction per second or for IOPS, as you can see, for small messages, we start with around, for one thread, around 1,800,000 transaction per second. And it went down when we hit the maximum bandwidth up to the limitation of the network card. I wanted to show another example with 8 IO threads as the system is scaling out. With 8 threads on the same, we used on the same PCI cores, so that on the same PCI that the same NUMA with the same PCI is used, and we split it four of the threads into one port, and four other threads work with the other port. We reached 9 million transactions per second with Connect IB. As for latency, again, on the same machines, we got less than 3 microseconds with 1 kilobyte messages on one thread, and we keep that with also a full transaction ping pong latency up until we reach the maximum bandwidth. So as you can see, the system is scaling out. Everything is working in parallel. We use parallelism to maximize the system resources. Let's talk about latency under maximum load. So under maximum load, we can see that on single port with one I/O thread, we are under 30 microseconds for and we got 1.8 million I/O messages per second. So this is a very good number. We can see that the line is it's a point where the line is becoming congested. And as we scale out to 8 I/O threads, we get up to 44 microseconds, and we got 9 million messages per second. I want to summarize it. As I said before, it's an open source project. The project was initiated by Mellanox. We are looking for partnership from other vendors or anyone who wants to join this effort. We think in the long term, the API take our client very quickly to market. They don't have to do all the writing again and again by themselves, and everyone in the industry can contribute its own effort to and share it with the community, so everyone will benefit. Again, the website is accelio.org. The code can be found in GitHub Accelio. Bug tracking and community is on launchpad.net. The email that can be used to send messages is info@accelio.org. I want to say a few words about the license. So we started with a BSD license, which is the most easier license that exists, maybe BSD or Apache. But we had to come up with a GPL v2, since we have a common code with the user space in the kernel. But as you can see, it's a dual license, so application provider can choose whether they like to work with the BSD license or the GPL license. Thank you. Any questions? Yes, please.
Have you written or done anything with the MPIs to this interface?
Actually, Accelio was not written in the MPI emphasis. It was written for mostly as a reliable connected QP. So we usually tended to the world of storage. For MPI, we work with MXM. We have a solution for that. We were not intended to work with MPI, but you know, if you find it suitable for your MPI, some of your API application, you can you can take it and use it. But it was not actually performed for MPI. I think MPI have other requirements that this API is not providing them, most of them or some of them. But if you find it suitable, feel free to use it. Yes, please.
So as far as HDFS integration is concerned, how is this related to UDA?
So it doesn't relate to UDA. We came up with another solution. We took Java from ground up and we wrapped Accelio. This was the first intended. We know that our clients that are looking for a Java API code that it is publicly released. We didn't find any. We know that there are a solution for Java. One of them was it's a commercial product that you can reach. Now we know that the Java itself API got some support for RDMA. So we wrote this API, and we started to look for a problem in the industry. So we know that there is we look for Hadoop, and we look for Cassandra, and look for other solutions in the system, and we try to dissect and find what's bothering those applications to get a better performance. So we start from the application usually, when we're not starting from the hardware. We change the hardware to give the application the best performance that it has. So that's what we did. We now have a solution for Hadoop. You can find out more information about it if you came up to me offline, and I will connect you with that. But there is a solution now that we know that it's working, and we're getting a very good result with that. Yes, please.
I believe these APIs are hardware independent, because these are written over the Works API. So whatever is supported by Open APIs, those hardware will be supported with these APIs. Whether these APIs use any hardware specific features.
We don't expose the hardware outside unless you need to do some tuning. So you get, like say, sets of API, so you can do a tuning, but you don't have to know what's going on beneath. You just have to take a message, send it from one side to another side, and you want to get the best performance there is.
Like Open supports IP and Rocky, and also supports various vendors like Mellanox. So these APIs will also support all these.
Right, because those API are written above verbs and the RDMA CM. So if you get them transparently, you don't have to do anything for that. We know that there are customers that are working with soft IRAP. He wanted to develop on his computer, and he's doing that. And we know that it's working on Rocky, it works on IP over IB, and so forth. It was tested, and it's working seamlessly. Yes, please.
In your examples, you specified a URL. Do you intend that to be expanded to even a GIT or a LID, or is that always going to be a host name or IP?
We are working above RDMA CM, and we're not working directly with verbs, so it's usually an IP and ports. Yes, please.
There are now load balancers available for user space applications to make it easier to use the Bars API with its RSockets and Accelio. Can you comment how to make a choice between these two libraries?
So I think that I didn't work with RSockets. What we come up is that we took applications and try to understand what bothering them, how did they want to work. We come from the application side of from the point of the application, and drill down to what we have with verbs, what we have with RDMA, and how to combine all of them to provide an application, an easy to use API, and not to mess them with a lot of detail of RDMA. Some application needs that, and that's what we were focused about. So RSocket is another issue. It's very strict API that is a socket API. We are not socket. We are providing much more services. We're providing message cancellation. We provide the delivery receipt. You can send a message to the other peer, and it's going to a synchronous operation, a longer synchronous operation. You want to know that it was delivered. So on the client side, you will be able to release resources, for example. So we have other services that are not given by the standard socket. Usually you have to develop them above sockets. It's more like a middleware and not like a simple API. We will provide multipathing. We will provide a connection reliability. When connection is disconnected, we will try to do exponential backoff to recover that connection. If it will not go, then we will try other scheme to go to another QP or available connection. If that won't succeed, we will do some kind of multipathing to reestablish a connection, send the messages. Messages are reliable. They will be sent. If that all fails, then application will get notification. But application doesn't have to write all these features again and again and again. It can be served by the middleware or by the network stack, and not by the application. Any other question? Thank you very much.